All right, so this is worksheet number 3, the multiple choice questions on the back of it. And we're going to get the answers to those questions by looking at the reduction potentials table in our book, in our data booklets. So just before we can answer those questions, let's look a little bit more closely at this table. Can you guys think of well, actually, I'll just tell you, a common redox reaction that everybody at some point in high school has seen happen? We've all seen, think back, either taking a piece of zinc metal, circle the zinc metal on your chart, or a piece of magnesium metal. You could also circle magnesium if you want, just do one or the other. I'm going to do the zinc. We've all seen the reaction where you put a piece of zinc metal or magnesium metal into acid, hydrochloric acid. What happens when you put the metal in the acid? Anybody? Nobody remembers. If you put a little piece of silver colored zinc or silver colored magnesium into a test tube with hydrochloric acid, don't you see bubbles of gas forming? What gas is that?
Hydrogen gas.
It's hydrogen gas, right? A grade 11 language, if you want to write at the bottom of your page, we're taking zinc metal and we're putting it with hydrochloric acid. A single replacement reaction is happening. It produces hydrogen gas, which we collected in grade 9 science, and we did the little flaming wooden splint tests, right? The whooping sound as it exploded in our test tubes. And it also produced zinc chloride, didn't it? In fact, in grade 9, that was what we were trying to do, create zinc chloride. What was the zinc actually reacting with in the acid? Was it reacting with the hydrogen ions or the chloride ions? Well, the hydrogen ions, if you look at it from a grade 12 perspective, hydrogen ions are going from +1 to 0 oxidation state, aren't they? While the zinc is going from from 0 oxidation state to 2+. The chloride ions aren't really changing, are they? They were -1 at the beginning, they're still -1 at the end. The chloride ions are arguably just the spectator here, aren't they? The actual reaction is a redox reaction. Zinc is reacting with hydrogen ions and creating hydrogen gas in zinc 2+. This reaction from our observations in the lab is spontaneous. When you put the zinc in, it dissolves completely. The zinc metal, it has a huge equilibrium constant, right? You get tons of hydrogen gas. So go on your chart, circle hydrogen ions in the middle of the chart. Hydrogen ions become hydrogen gas. Circle the hydrogen ions. Now, we have just established, connect those two things you circled. We have just established a pattern on this table, a pattern that we can now use as a shortcut. I know from experience that this reaction, zinc metal with hydrogen ions, is spontaneous. It reacts. It has a huge Kc value. It must have a positive cell potential if I calculate it. But what pattern have we just seen on the table? Something on the left is being reduced here. And as it gets reduced, it's reacting with something on the right side and below it. Do you see that? Something on the left, hydrogen ions, are reacting with something on the right side below them. That pattern means anytime you see that pattern on this table, you will get a positive cell potential. You'll have a spontaneous reaction. So can you see that acid would also have reacted with magnesium metal in the same way?
Yeah, because it has the same sort of pattern.
Give me another metal that would have reacted with the hydrochloric acid the same way.
Aluminum.
Aluminum metal. Now, practically, aluminum has a bit of a problem. The surface of aluminum metal has aluminum oxide on it, which sticks to the metal. So you'd have to scrape that oxide off, then it would work. What's another one? Common metals that would react with hydrochloric acid the same way.
Manganese.
Okay, that's not that common, but yes, manganese would work. How about iron? How about nickel? How about tin? Right? These would all work the same way, right? Alkali metals down below. You wouldn't want to handle alkali metals. They're explosive with water around, but they would react in the same way. They'd explode, but they would react the same way. Give me a very common metal that would not react with hydrochloric acid in that way. Give me a very common metal that does not react with hydrochloric acid because it doesn't follow that pattern. Okay, silver, but silver is not that common. Silver is very expensive. But yes, so silver would not work.
Copper?
I was thinking copper, yes. Copper metal does not react with hydrochloric acid that way. But didn't we do a lab last year? Maybe it was a virtual lab, actually. Do you remember the percent copper in brass experiment? Vaguely. In the video, I took a piece of brass, which has copper in it and zinc in it, and I put it into an acid, and it did react. But you remember what it looked like as it reacted in the video? Anybody remember this? When I put the copper into the acid, I did it in a fume hood. Nobody remembers my amazing video? It reacted and turned to a reddish brown gas. Is that coming back to you?
think we didn't
Here I
talk.
thought I made this amazing impact with that video. Clearly I didn't. So copper, although it does not react with hydrogen ions like hydrochloric acid, find me an acid that copper would react with. So copper's on the right here, isn't it? What's it going to react with? Anything on the
Left side.
left and above it. So do you see an acid? Hey, I just see it right here. Nitrate ions with hydrogen ions. Wouldn't that just be nitric acid? Right here, NO3 minus and H plus.
Yeah.
So copper would react if you put it in nitric acid. Now, does it produce hydrogen gas? No, it produces NO gas. And the NO gas immediately goes with oxygen in the air to make NO2 gas. And that's the reddish brown gas that was in the reaction. So copper won't react with hydrochloric acid, but it does react with nitric acid. In fact, all the metals that reacted with hydrochloric acid would also react with nitric acid, wouldn't they? Would silver? Does silver react with nitric acid the same way?
Yes.
Yes, it does. Give me a metal that does not react with nitric acid like that.
Gold. Gold.
Gold. And gold is often considered a noble metal because it doesn't react with very much at all. Would anything react with gold metal?
Yeah. Fluoride.
Well, looking up above, not fluoride, but
Fluorine.
fluorine gas would react with gold. Hydrogen peroxide in an acidic solution would react with gold. So does permanganate ion in an acidic solution. Right? How do I know it has to be in an acidic solution? Because it says H plus beside it, right? If I just put gold into a permanganate solution, nothing would happen. But if I add some acid to that, boom, it starts reacting. Okay, do you see how this is working? How this pattern? Now, is it magic? Something on the right reacts with something on the left above it? Is that magic? No.
No.
If you do the math, like look back at our original reaction. Hydrogen ions are making hydrogen gas. What's the potential for that? 0 volts, right? That's its reduction potential. What is zinc's oxidation potential? Positive 0.76 volts. So what do you get if we put those together? You get positive 0.76 volts. And the point is you get a positive potential, don't you? Whenever something on the left reacts with something on the right below it, you get a positive potential, which gives you a spontaneous reaction. Why do they not react if they don't follow that pattern? Because you'll get a negative potential, which will have a very small Kc. Why do they have to be on opposite sides? Why do the reactants have to be on opposite sides of the table?
One has to be an oxidation and one has to be reduction.
Yeah, one guy's got to be oxidized and one guy's got to be reduced, right? So you got to have opposite sides of the chart. All right, so with that, hopefully understanding, go look at these multiple choice questions. Actually, one more thing before I go here. Did you notice, so everything on the left is being reduced, isn't it? They're gaining electrons. What can you say about fluorine at the very top? It's got the biggest reduction potential, doesn't it? So fluorine would be the most easily reduced, wouldn't it? Now, what do you call a thing that gets reduced?
Reducted.
Reducted.
An oxidizing agent.
That's what I was looking for. It's the oxidizing agent in the reaction, isn't it? So if fluorine is the most easily reduced, because it has the highest reduction potential, then what can you say about fluorine as an oxidizing agent? It must be a really, really strong oxidizing agent. In fact, it would be the strongest oxidizing agent, wouldn't it? Now, what do you call the things on the right side of the equations? They are being oxidized as you read the reactions backward, aren't they? So the things on the right are reducing agents, aren't they? Where's the strongest reducing agent? The strongest reducing agent would be the one that's most easily oxidized. So it would have the highest oxidation potential. So where would you find it? It'd be lithium, wouldn't it? Not lithium positive, lithium metal, Li. Do you follow that? If you look at the arrows on the side, the arrow on the right points down, right? The arrow points down, and it says increasing ability for reducing, more easily oxidized. And at the very top of the chart, it says the things on the right are reducing agents. The things on the left are oxidizing agents, right? Okay, so a lot of stuff on that chart. Then let's answer question number 3.
Is there a reason why people don't use fluorine gas and lithium metal to make batteries?
Well, fluorine gas is, number one, using gases can be challenging. Lithium is also, there are lithium ion batteries, but lithium solid would be hazardous. And the fluorine gas would be toxic, highly toxic. So there's other considerations as well.
Oh, okay.
Number 3, we were talking about this battery earlier. Magnesium metal and magnesium ions in our anode, tin and tin 2+ in our cathode. Which of the following was true about that cell? So would magnesium get heavier over time? Magnesium was the anode, wasn't it?
Yes.
And the anode gets oxidized. So what's the reaction happening there? Mg is becoming
Mg2 positive.
and losing electrons. So magnesium metal is a reactant. So would that electrode get larger or get smaller?
It would get smaller.
Magnesium is a reactant, it gets used up. So yes, the magnesium metal would get smaller. So this magnesium gets heavier, that's not true, right? We get lighter. What's happening at the other half cell? Well, that's reduction. So the tin 2+ is gaining electrons to make tin metal. So at the other electrode, tin metal is being produced. So the other electrode would get heavier, wouldn't it? The tin would get heavier. But part B says the concentration of tin increases over time. Does the concentration of tin increase over time? Is tin a reactant or a product?
It's a product, so the
Tin,
concentration would decrease.
10 plus. Is it a reactant or is it a product? The 10 plus
That's a reactant.
is a reactant, isn't it? So will its concentration be going up or going down? It'll go down. Reactants get used up. So the tin concentration would increase over time. That's not true. Cations flow from the salt bridge towards the tin. Is that true? Do cations flow from the salt bridge towards the tin? Well, tin is the cathode, isn't it? Gets reduced. Do cations move towards the cathode? That's why it's called the cathode, isn't it? Because yes, cations go towards the cathode. Anions go towards the anode. That's why they're called cathode and anode. So is that true that cations go towards the tin? Yes, that's looking true. Do electrons flow from tin to magnesium? Well, magnesium is where they were being oxidized, right? Oxidation was occurring there. And that's the loss of electrons. So electrons are leaving from the magnesium and headed towards the tin, aren't they? So that last statement was false. All right? All right. For the next questions, refer to your table that we were just looking at. So which of the following is most easily reduced? The table we have is a table of reduction potentials, isn't it? So can you translate that phrase, most easily reduced? Can you translate that to say something about the reduction potentials? If you're most easily reduced, you must have the highest
Reduction potential?
potential. So before you just pick an answer, which side of the chart, left or right, would it be on if it has a high reduction potential? Things on the left side are being reduced, aren't they, on this chart? So if it's not on the left side of the chart, it's not being reduced. So it could not be the answer. So it has to be on the left side, and we want the highest potential. So something on the left near the top, hopefully. So which of those choices is the best choice? What's the answer? It looks to me like gold 3 plus is the best answer, isn't it?
Yes, the nearest to the top.
Okay. Not just near the top, but near the top and on the left, isn't it? Okay.
Yeah, it's the nearest to the top for the oxidizing agents.
Okay. Which of the following is the strongest reducing agent? Well, strongest reducing agent, what happens to reducing agents? They get oxidized. So if you want the one that's the strongest reducing agent, you'd want the one that gets oxidized most easily, wouldn't you? So then what kind of oxidation potential would it have if it's the most easily oxidized?
A high one.
Yeah, you want a high oxidation potential. So what side of the chart am I looking for? Left or right? To be oxidized, it would have to be on the right, wouldn't it?
Yes.
And if I want the highest oxidation potential, would it be near the top or near the bottom? Remembering you change the signs, right, when you pick the oxidation potentials. So it's going to be on the right and near the bottom, isn't it? So which one of those guys would be the strongest reducing agent?
It would be sodium, right?
There's two sodiums here. Which one would it be?
The non-ion. Just sodium metal, I suppose?
Sodium metal, right? The neutral sodium. Everyone understands why? Okay. Which of the following would be capable of reducing lead 2 plus to lead metal? So I'm going to go find on my chart this reaction. Lead 2 plus gets reduced and makes lead metal. I'm going to go find that reaction. And whatever I'm going to pick has to react with the lead 2 plus. Well, the lead 2 plus is on the left side of the chart. So what will it react with? Anything on the right
Right
side
side and below it.
below it. So which of these choices would work?
Zinc metal.
Zinc metal, is that right? Yeah, I think so. But isn't magnesium also below it?
It's on the left side.
Well, this is not just magnesium, this is Mg2 plus. So no, that would not work, right? Is this making sense, folks? Which of the following could oxidize Fe2 plus to Fe3 plus? Well, my chart is a reduction chart. So I'm on my chart, I'm going to find this reaction, aren't I? That's the reaction that's going to be on my chart. But what do I want to react with this? I want the Fe2 plus to react, don't I? And the Fe2 plus is on the right-hand side. So what would it react with? Something on the left side and above it, right? So which of these would it react with? Fe2 plus, it would react with which one? Try to find the.
I put
Oh, there it
zinc 2 positive, but I don't know if that's right.
No, it's zinc's not going to react with it at all, is it? Zinc is below this reaction, isn't it?
Oh,
Fe3,
it's got to be above it.
Fe3 becomes Fe2 plus. Since Fe2 plus is on the right, it's got to react with something above and to the left. So of the choices there, I think I see the answer. It's chlorine, isn't it? Now, can I just point out, even if you knew nothing about this chart, you didn't understand it all, aren't three of these guys on one side of the iron equation and one of them on the other side?
Yeah.
Chlorine's the only one above and the other three choices are below. So has to be chlorine. Okay, but I hope you actually do understand it. Which of the following is the strongest oxidizing agent? So if it's an oxidizing agent, it's getting reduced. It has to be on which side of the chart?
The left side.
The left side. And if you want the strongest oxidizing agent, you want the one most easily reduced. So it's going to be on the left end near the top, isn't it? So
Yes.
is the answer again chlorine?
I think so.
Good. All right. People do traditionally struggle a little bit with those kind of questions. And those are common multiple choice style questions. All right. Let's move on to question 4. Have a calculator with you, have your data booklet open. All right, so we've got this voltaic cell. I see titanium, I see nickel, 1 molar titanium, 1 molar nickel. This is the standard cell, right? Which electrode is the anode and which is the cathode? So you might be looking at your chart in your book, but titanium's not on our chart, is it?
Doesn't look like it, but it shows us the electron flow.
Hey, it shows the electron flow. Why does that help me? If the electrons are flowing in this direction, then what's happening at the nickel? What's happening at the titanium? Electrons are moving towards nickel. So nickel, is it gaining or losing electrons?
Is gaining.
The nickel is where electrons are being gained. And if the electrons are leaving the titanium, then the electrons are being lost there, aren't they? So which electrode is the anode, which is the cathode? The titanium is the anode. Electrons are lost there. The nickel is the cathode. Electrons are gained. And I'm not just saying it as definitions. I can see the direction of the electron flow, right? So then label the charges. Now, how do those physics people label the charges? Because electrons are leaving titanium, they said it was negative, has lots of negative. And because they're moving towards the nickel and electrons are negative, they said that must be positive. Opposites attract. So then write your half reactions at each electrode. Do you agree with what I wrote? What's happening to the mass of each electrode? Okay, so don't overthink that. If the electrode's a solid and it's a reactant, then it's getting used up, isn't it? The mass would go down. If the solid is a product, then it's being produced. It's going to increase in mass. So which one of the two metals is the reactant and which one's the product? The titanium is the reactant and the nickel is a product, isn't it? So this is a reactant. Mass decreases. Nickel is a product. The mass increases. So what happens to the concentrations of the two ions? They both began at 1 molar, but as the battery operates, will their concentrations go up or go down? Well, again, don't overthink it. Look at it. Is it a reactant or a product? Titanium 2+ is a product. Nickel 2+ is a reactant. So the titanium is a product. The concentration increases. The other guy is a reactant. Okay. Give me the overall reaction for the cell. Just take your two half reactions and put them together. So it's easy, everything gaining 2 and losing 2. You don't have to multiply by anything. And then use the information in the diagram as well as the data booklet. What's the standard reduction potential for titanium 2+? What information in the picture can we use to help figure that out?
We're given E cell.
Yeah, so we're given the standard cell potential here was 1.37 volts, weren't we? And what can we get from our data booklet?
The one for nickel.
So what's happening to nickel in our battery?
Is being reduced.
So we would want nickel's reduction potential, wouldn't we? Yeah.
Yeah.
So the cell potential would equal the oxidation potential for titanium. You with me on that? Plus the reduction potential for nickel 2 plus. Is that logical?
Yes.
Plug in what we know. So the cell potential is 1.37 volts. The oxidation potential of titanium, I have no idea. Titanium is not on my chart. It's not in my booklet. But nickel's reduction potential is in my booklet. That's going to be, Dan, what is it? Negative 0.24 volts, which means the oxidation potential for titanium is going to equal 1.61 volts. But wait, we didn't want the oxidation potential. We wanted the reduction potential for titanium 2 plus. So therefore, the reduction potential for titanium 2 plus would equal negative 1.61 volts. What direction does the potassium ion flow from our salt bridge? The salt bridge has potassium nitrate in it. So there's potassium ions and there's nitrate ions. What direction will the potassium ions flow here? Do they go towards titanium or do they go towards the nickel, the potassium? Well, we said the potassium, is it a cation or an anion? Potassium. It's a cation. So cations go to the cathode, and nickel was the cathode, wasn't it? So there's our answer. So K plus is a cation, goes to the cathode, it goes to the nickel 2 plus half cell. And give the description of the cell using line notation. Give you a moment to do that and check your answer. Okay, do we agree? So line notation, the anode goes first. So the titanium metal strip is in a solution of titanium 2 plus. Salt bridge, on the other side of the salt bridge is the nickel solution, which has a nickel strip in it. Okay. Can we finish today by about 5 minutes, I think, looking at my clock? What is the, let's draw and label a standard cell with lead and magnesium. And we're going to label all these things on the side. In my drawing, I'm going to do something a little bit different. Okay, so you might want to sketch what I'm going to do here. I've shown you a cell where there's two beakers side by side connected by a salt bridge, right? That's a very common way of constructing these cells. Here's another way. Take a beaker and put one solution in it And instead of another beaker and a salt bridge connecting them, take what's called a porous cup. Porous cup. Sort of like if you have house plants at home, do you have any flower pots made of terracotta? Like a ceramic? What color are those things? Brownish red, rusty colored. Do you ever notice with those terracotta cups, if you water the plant, the outside of the flower pot sort of gets damp? Ever notice that? The terracotta is a clay and it's porous. It lets water move in and out through the clay. So if you use a porous cup, then what don't you need anymore? What do you no longer need if you are going to use a porous cup? You no longer need a salt bridge, do you? Because the ions can move
Through the cup?
through the cup. So there's no need for a salt bridge. The porous cup lets the ions move back and forth through it.
Is it just the ions that can move, or does some?
And water, of course. So
Okay.
let's put, it doesn't really matter. I'll put the lead strip outside. And what's the lead strip sitting in? 1 molar. Now again, remember I said 1 molar lead 2+, but what does there have to also be in there? Well, besides water. There has to be some kind of nitrate or chloride ion, doesn't there? You can't just have lead 2+. It has to have a salt of some kind. So we don't show it, but there are other ions in there, anions, and that's an example of an ion that can move in and out of the cup, isn't it? Right? And then what do we put inside the cup? Put the 1 molar magnesium 2+, again, with some kind of anion, and a strip of magnesium metal, and connect the 2 electrodes with a voltmeter. Okay, so there is another common setup for a voltaic cell. The porous cup serves as the salt bridge. You might want to note that. Ions can move through the porous cup, so there's no need for an extra salt bridge. Okay. All right, I'll stop there. If you feel like finishing that, or actually no, we'll just pick up here tomorrow. I've activated a web assignment so that something can work on.
Please contact the office, Ms. Mallon.
All right, folks, have a good evening. For those of you at home,
Have a good day. Thank you.
take care.
Thank you. Have a good day.
Have a day.